we can easily construct an unscaled graph of the area of a square versus length of a side of the square. We start with a small square. We sketch a square whose sides are double that of the small square. And we observe that if we cut the square in half this way and in half this way, each of these small squares is equal in area to the original square. Because simply, if we've doubled the side, then when we cut that doubled side in half, we get the original side. And same thing on this side. Okay, so and this shows that we have 4 times the area. So we have area okay, I'm going to use, okay, let me back up. Okay, my reason for hesitation is I don't want to use A because A is generally used for something else with power functions. So I'm just going to use area U for the small square. And we could call that the unit of area. The area of this square is our unit of area. So here the area is what? Well, there are 4 squares of area U, so the area is 4U. Now, if I double this one, okay, double this one, the sides are going to be, oh, about this long. Let's see, that's about twice, isn't it? Yeah, it's pretty close. Okay, so if I double this square, it's going to look something like this. If I cut the sides in half, then I have my doubled square. Of course, each of these 4 doubled squares has area 4 times the area of the original square. So the area is 4 times 4U, which is 16U. Now I could double this one again, and it's clear that we would get area 4 times 16U, because if I double this, I'm going to be able to break that doubled square into 4 parts, each of which is 4 smaller squares, each of which is equal in area to this square. I'm not going to do that. I'm just going to go with the 3. So if I construct a graph, what's happened? Well, I start with area U. Now I could use any unit there. It doesn't have to be, this distance doesn't have to equal this distance, although it kind of looks like maybe it does equal this distance in this case. And actually, let me back up. This unit here will stand for the length of a side. So, side length. And we'll let this be the length of the side of the small rectangle. Again, it looks like it has that length, but that's not necessary. We could use any unit we want here. Okay. Now, we need to represent an area. So we want the area of the square. Well, that's going to be U. And we can draw a point on the graph then of area versus side length. Now, the next side length is twice as great. So we've doubled the side length, and then we're going to double that again. So we just take this and we double it. And then we take this side length and double it. I think that puts us out about here. I went a little too far, but you get the idea. Okay? Now, what's the area? The area for the doubled side is 4 times whatever the U is. So we're going to have to come up here, 2, 3, 4. And that's going to put us here. Now we double the side length again, and we're going to have to get 16 times the original area, 4 times this area. So we're going to have to do this 1, 2, 3, 4 times. That puts us, well, way up here. And if we put that above our point for the side length, we see that our graph looks something like this. So, to use a different color, our graph will do something like this. It's not a particularly well drawn graph, but it sort of works. Now, what's the rule for this graph? If we take 2 side lengths, say this length and then double this length. Okay, let's see. Okay, right here is the y-coordinate that represents the area of this square. And if we come up straight up from here, we get to about this point, and that's going to represent the area of the new square, of the doubled square. So I can draw this arrow, and I can draw this arrow. What's the y factor? Well, we can see we got one of these. If we did 2, 3, 4, we would be up about here. So that it appears that the y factor is about 4. So if x doubles, or if the side length doubles, which we could call side length, which we could call x, if this doubles, then area, which is y, fourples. Now, of course, this is completely so. If we double the side length of a square, the area fourples, because whatever the side length is, if we double it, we get a square that can be broken into 4 smaller squares, each equal in area to the original one. So doubling any square fourples, quadruples, the area. That's consistent with the graph. And what we then have is the fourpling graph. So this is now the fourpling graph. The rule for the fourpling graph is that y is going to be ax to the p. I include the a here because we haven't yet scaled this graph, and we could use any scaling we need for the x-axis and any scale we want for the y-axis, and we would get a perfectly valid graph representing the area versus side length. Okay, so y equals ax to the p, and of course we know that 2 to the p equals the y factor, which equals 4, so that what power of 2 equals 4? Well, that implies that p has to equal 2. So now we know that y equals ax squared. So that the graph for the area of a square versus length of the side is some multiple of x squared. Y is some multiple of x squared. Now we can talk about scaling this graph, and we'll do that in a subsequent video.